In this lecture, we continue with our discussion surrounding measurement error and how it is related to reliability, and we'll also get into the introduction of ways to document reliability. Beginning with our issue related to measurement variability or measurement error, there are three main sources of measurement error that are involved in research studies. The first one is the rater, and the term rater is referring to the actual researcher, the person taking the measurement. Now, this also applies to clinical situations as well. And so when a clinician is taking a recording, a measurement such as blood pressure or reading diagnostic tests, that person can often be the source of that measurement variability. The second is the actual tool used to measure some variable of interest. And typically, measurement instruments that are more complex, that have multiple steps or moving parts, if you will, do run the risk of increasing the variability that can be obtained measurement to measurement. And the third major factor that contributes to measurement error is the actual item or the actual variable that is being measured, the characteristics. So two examples here are measurements of blood pressure, measurements of blood glucose. These two physiological measures do inherently vary day to day and do vary within a particular day. So when taking measurements, repeated measurements, it is important that such measurements as these be taken at the same time of the day under conditions that are as close to each other on that day-to-day basis. But reliability should be quantified in research studies, and one way that that's been used in the past to document reliability that is inherently limited is by evaluating the correlation, the relationship between two variables. The specific statistic used to assess correlation is the Pearson product moment correlation coefficient, or summarized as the PPMC, and I'll make reference to that in the subsequent slides. So the Pearson product moment correlation coefficient, as a measure of correlation, reflects the degree of association between two sets of data, and sometimes this is used as a measure of reliability, but it is very limited, and we'll go through why the Pearson product moment correlation coefficient is limited as a measure of reliability. So on the left hand side here we see a relationship between two sets of data. So we have our predictor variable along the x-axis and our criterion, or sometimes referred to as the dependent variable, along the y-axis. And what we see here is a perfect correlation. So the correlation statistic is an R value. Sometimes the R value, the symbol, is used as an uppercase R or a lowercase r. So those two symbols are used interchangeably. And here we see a perfect correlation. So here we see a one-to-one association between data along the x-axis and data along the y-axis, and it forms this perfectly straight line, and the individual data points lie on that line. And so this would, if we rely on the correlation coefficient as a measure of reliability, this would suggest that these two variables are perfectly reliable. However, if we take a look at the right-hand side here, we see, as we have on the left, a perfect correlation between the x-axis and the y-axis, as all the observed data points lie perfectly on this straight line. However, notice that the second score, the score along the y-axis, is shifted upwards by 2 units. So despite the fact that we have a perfect correlation, the variability between the x-axis and the y-axis there is a variability that exists by 2 units. And so if the x-axis represents a measure of blood glucose on day 1, and this measures blood glucose on day 2 along the y-axis, the measurement on day 2 of blood glucose is shifted upwards by 2 units. And so we have that variability, but the Pearson correlation coefficient would suggest that it's perfectly reliable, while there is a difference from day 1 to day 2. And so to understand reliability, we have different measures of reliability coefficients, and essentially the reliability coefficient is a ratio. And it's a ratio between the standard deviations, or the sigmas, of the true score divided by the variability of the total score. And recall that the total score is a combination of the true score and the error of that variability, of that standard deviation among a set of scores. So if the scores do not vary, if the error term drops to 0, then we end up with a ratio of the true to the true, and we have a perfectly reliable set of measurements. And so the smaller the error that exists in a set of scores, the larger the reliability coefficient will be. And so if we take a look at some hypothetical values, if we have a reliability coefficient of 0, that would suggest there's essentially no reliability. Contrast to that, a value of 1.0 would suggest perfect reliability. So the lower the error, the less error, the closer the true score that we see here is to the observed score. And so in terms of reliability estimates, we do have some guidelines. And so measures that have reliability coefficients less than 0.5 are typically considered to be poor in terms of the reproducibility of that measurement, or the reliability of that measurement. Measurement tools or testing instruments that have reliability coefficients between 0.5 and 0.75 are considered to have moderate reliability, and measures above 0.75 are generally considered to have good reliability. So the type of statistic that is generally accepted to produce the most valid measures of reliability include what's called the intra-class correlation coefficient, and we'll address that here on the next slide. But we begin here with the interclass. So inter means between. This is our PPMC. And so the PPMC, as outlined previous, is limited in terms of providing reliability. And so it really isn't a good measure of reliability. The first reason that we see here, that is a review of the previous slide, is that in this demonstration we have a correlation coefficient that's perfect at 1.0, but the scores are shifted along the y-axis by 2 units. And so the reason that the PPMC is limited is because it's only bivariate. Bivariate means that the Pearson product moment correlation can only examine the relationship, the association between two variables at one time. So oftentimes we have multiple measurements of some measure of human behavior or some physiological measurement, but we have to be able to examine reliability if we have more than 2 measurements. The Pearson product moment correlation coefficient, the interclass between variables, cannot separate variance components. And so the correlation coefficient would not allow us to examine how much error can be expected across multiple testing. Recall that all measurements inherently have variability, but what we want to be able to document and quantify is how much variability we can expect. Two sets of scores can be highly correlated but still be significantly different, and that's what we see here on the graph on the left hand side. So here we see two scores, one set of scores along the x-axis, another set of scores along the y-axis that are perfectly correlated, but they're not the same score. You don't get the same score along the y-axis that you do along the x-axis, as these scores are shifted vertically. And scores may be poorly correlated, but not significantly and not be significantly different. So we do see these sorts of issues related to using the correlation coefficient. A statistic that is widely used in terms of documenting reliability is called the ICC, or the intra-within class correlation coefficient. This is similar to the Pearson product moment correlation coefficient in that the ICC values range from 0 to 1.0. It's different from the correlation coefficient, the Pearson, because the ICC is computed directly from variance estimates. The intra-class correlation can be used with more than two measurements as well, and the degree of test-to-test variability can also be calculated as by what's called an SEM, or a standard error of measurement. And so in this lecture we won't go into the mathematics of this, but with an ICC we can get this coefficient that would indicate the degree of reliability, but also get a degree of expected day-to-day or test-to-test variability. This approach requires the calculation of a statistical procedure called the analysis of variance that we won't get into in this course, but it is a statistical procedure that compares sets of scores that are taken on a numerous basis. And the SEM, or the standard error of measurement, is a statistic that points to how precise a test is of human behavior or human physiology in tracking that trial-to-trial variability. So if we're talking about measuring something repeatedly, we do have to have an indication of how reliable that measurement instrument is, and the ICC and SEM are the test statistics of choice when quantifying reliability. So this ends this brief lecture, and in the next one we'll get into a couple of applications of test-retest reliability.